Hello, everyone. Welcome to another Hardware.io webinar. My name is Antriksh, and I'll be the host for today's webinar. I'm glad to welcome Stephane, who will present today with us on embedded kernel emulation in QEMU for security assessment. Stephane is a security expert at AIRBUS Labs. Some of his publications are on kernel exploitation, offensive and defensive virtualization approaches, and recently adapting state-of-the-art fuzzing technology to simulation environments. In today's webinar, Stephane will explore whether it's worth investment in QEMU internals to support emulation of a target firmware. Some house rules for today's webinar. The webinar presentation will be for 30 minutes, followed by 10 minutes would be available for Q&A. If you have any questions, attendees, please send them across via the Zoom chat window. I will be moderating them, and after the presentation is complete, we will answer the questions. Also, this webinar will be recorded and uploaded on our YouTube channel for further view. Now, I would like to invite Stephane to begin his presentation.
Thank you. Can you see my slide?
Yes, yeah. Full screen. Yes, thank you.
Okay, perfect. So I'm Stephane Duverger, and I will be talking about QEMU and how we can take benefit of such an amazing simulation environment to do security assessment for very specific embedded firmwares. And so first, who am I? I'm a security researcher working for AIRBUS Several. I'm absolutely not specialized at hardware security. But recently, I've been working on the analysis of the security of a safety critical kernel. And we happen to create a tool to fuzz it with Anaïs Ganté, which has been presented in a French security conference, the STIC. The tool is named Gustave. And after that, since the tool was based on QEMU, I happened to write a deep dive blog on QEMU to give some experience return on deep diving inside QEMU. And so this webinar is about attacking embedded firmwares with QEMU. So I will give a brief look of some existing approaches that are available since the last couple of years. And we will discover that many of them are actually based on QEMU. We'll also dig a little bit inside what we call in the aircraft industry, the avionics equipments, and how we can easily simulate them using QEMU, at which cost and which complexity, and how repetitive they could be. And if QEMU will allow us to implement further some attack frameworks or interact with the fuzzing engine, for instance. So I will go a little bit inside through the development process. And then once we will be able to reach an interesting point, thanks to the emulation in a specific firmware, then we will start doing some security stuff. And so for the existing approach, I think a lot of you are pretty familiar with, for instance, AFL Unicorn. When you are targeting embedded firmwares, AFL Unicorn is useful if you want to focus on a very specific part of an algorithm, a file system driver, a parser located inside a firmware. And so this kind of tool requires a lot of reverse engineering to extract the component that you want to attack. Additionally, you might need to be able to run the firmware on the real hardware to get the ability to extract a whole execution context to give to AFL Unicorn. So there are notable examples that has been published, especially at Zero Night, and we won't go further on that. The second approach is usually more global and trying to do a full system simulation. So it requires less reverse engineering, depending on the availability of some hardware specifications. But anyway, in the end, you happen to have a more complex simulation environment with the CPU and the devices. And so being able to run a full system is really interesting if you want to create some more complex attack scenario, or if some applications that you want to attack inside a firmware depends on a lot of other application and environments. And so there are existing tools to do that kind of thing, namely PowerFL, for instance, which is really comparable to Gustav. And recently, I had the opportunity to discover Hallucinator a little bit. And Hallucinator is a really interesting approach. It has been published in 2010 in Unix. And this is something which is targeting some complex SOC in the modern IoT and microcontroller world. Their approach is trying to rehost firmware and do some fuzzing with QEMU also. But they had an interesting observation is that a lot of modern firmwares running on that kind of SOC actually use hardware abstraction layer libraries provided by the SOC manufacturers, which can ease the implementation of the firmwares. And so their goal was to be able to identify and match these hardware abstraction layers to prevent complex device-specific emulation anytime they want to attack specific firmwares. And so by identifying this HAL, they are able to wrap these function calls and simulate them in an easy fashion using Python, for instance. So this is a very interesting approach, and it scales well if you have a lot of firmwares using this kind of abstraction layers. So I will give a brief overview about embedded firmware and specific operating system kernels in our aircraft industry. And the first thing I have to say is that usually we are facing firmwares which are really minimalistic, highly deterministic, and static by nature, meaning no dynamic memory allocation and things like that, no dead code. And usually each system that we have to analyze tends to be very specific to the equipment it is running on. And so we also usually have access to some hardware which is much more simpler than what we can find in modern SOC. And last point is that we also usually have access to the hardware specification. And so unfortunately, as avionics don't share hardware abstraction layer and don't even have some kind of things, we can't benefit from hallucinator approach, for instance. And so that's why we questioning ourselves, is it worth it trying to implement device simulation using QEMU? And as a strategy, how can we do something like hallucinator, actually? So the first thing that you can easily do is retrieve the full system memory map of your firmware environment and hardware definition and implement inside QEMU default memory wrappers for every memory regions defined in this specific equipment. And if you are not able to implement every devices, or you don't want to take care of any devices that are present on the board, maybe you will have to do some tricks and reverse engineering skills at trying to bypass some driver initialization that you discover inside the firmware. But we'll have some explanation on that later. And if we look at an example equipment in avionics, the so-called CPIOM, actually it's a pretty simple hardware environment. We have a PowerPC CPU with a PCI subsystem, SDRAM controller, some flash controllers too. And actually this is a very low complexity from a simulation perspective. There is no complex GPU, at least for that kind of equipment, or complex network controllers and so on. And so our interest into deep diving QEMU is actually in the security community and in the modern open source world too. QEMU is a major software. It's used everywhere, and especially in offensive security projects. And it's always good to have a look at how the tools you are playing with actually work. And when you look inside QEMU, you will discover that it has a lot of powerful APIs, a very huge code base with a lot of devices and board and CPU implementation. And it's also perfectly integrated with your working environment, meaning that you have access to tracing events, GDB server stub implementation, a monitoring interface, which could be seen as an extension of a powerful debugger for ring zero stuff. You have snapshot API and so on. So if you know how QEMU works and what it offers, this is absolutely endless for your imagination to implement additional things for security purpose. And so if we want to really look at how we can implement these specific devices for avionic equipment using QEMU, the first things you will have to do is developing a new board and new devices. And as I said, there is already a large code base in QEMU with a lot of examples. Additionally, you also have access to a lot of subsystems which are already present in QEMU, such as AIRBUS PCI. A specification is perfectly implemented in QEMU. You have a lot of APIs regarding the memory and access to the virtual CPUs. And as a metric, the basic implementation of a CPIOM only took me 2 man-week. And so what you will observe is that at first the learning curve of the internals of QEMU might seem erratic. You don't know where to start, you need pointers, but then it will grow really fast. The second point is that beside implementing new devices and boards, if you want to do more clever tricks inside the QEMU engine, namely hacking into the TCG, for instance, then this is actually a piece of work, but it's really understandable, and digging into that kind of component allows you to provide feedback to coverage guide it further, for instance, and even play with low-level aspect of a memory, as we'll see in the presentation. So maybe in the first place, what was missing is a big picture and documentation, high-level documentation of the QEMU components. And with some pointers, you are able to be autonomous rapidly. This is why I wrote this little blog with a simple and naive approach for security guys in the first place. And so the basic strategy we have at simulating a CPIOM is that usually you start by reading the specification that you've been given and analyzing the system memory map. And you will be defining some wrappers for every memory regions defining these devices, so that you will be able to trap anything that you have still not implemented the behavior. And so for sure, you will be able to have access to empty wrappers to log what piece of code have been accessing what portion of the memory. And if we look at a simple example, for instance, the SDRAM controller, you will look that you can easily map the full RAM of your simulated system for your firmware. And if this SDRAM controller also have some additional configuration register for security purpose or things like that, you can even, with QEMU, map some portion of the memory representing this register using IO memory region. It's only a single call to the correct API. And using that kind of memory region, you can define callbacks that will be called for every read and write operation on this very specific memory location. And so this is really interesting to prevent from doing a lot of reverse engineering and trying to run as much as you can. And when you detect something wrong, then you know where to look at in the firmware code. You can have a more general approach toward that kind of thing at defining generically any IO subregion for a lot of small areas, for instance, forbidden areas, reserved memory location, and things like that. And whenever you will be plugging a fuzzing engine to your simulation system, then you will be able to trap, thanks to that kind of callbacks, some access to forbidden areas too. Another example is that the first things that you will try to do when you implement devices emulation is to test them. And to test your emulation, you need a firmware with drivers that will actually interact with your device emulation. And if you have access to the kernel health image of your firmware or kernel, you will be able to load it directly with QEMU. It's no secret. But if you only have a binary dump from a Flash component, for instance, this is no big deal to actually emulate a Flash controller. First, because they already have some existing implementation in the QEMU code base. And actually, for instance, in our CPIOM and the PPC CPU, simulating the Flash for the code part is nothing more than giving on the command line of QEMU the file representing the content of your Flash and telling QEMU, okay, please map the content of this file as a memory region. And if you still also have some IO register related to your controller, then you will define some region. And we will see that it's just a couple of 3 to 4 functions from the API, nothing more. And then your firmware can boot. For the remaining part of the Flash itself, for data access or EEPROM or things like that, actually the implementation of basic Flash commands, read, write, lock and log, erase sector, does not take more than 175 source line of code. So that's really a small part to implement with no complex logic. As I said, there are a lot of existing subsystems available in QEMU, and PCI is a pretty good example. PCI is a specification, and QEMU developers provide anything you need to implement additional PCI device. The config space of PCI allows you to define some wrappers to dynamically intercept drivers trying to change bar register or things like that. QEMU is also able to remap dynamically memory regions for you. It's only a great pleasure to develop some PCI devices inside QEMU. There are still 2 major components and devices that you need to implement when you want to simulate a full system. The interrupt controller itself, and which is responsible for redirecting and managing priorities of IRQ. And inside QEMU, it's only some boilerplate with plugging the CPU IRQ lines to your interrupt controllers to finally the devices that will be responsible for triggering and raising interrupts. And in small and embedded components like CPIOM, the interrupt controllers are no more than a set of bit fields with priority, masking, and pending. So it's really not complex to implement. Maybe the most complex part might be related to timers implementation. Timers are really mandatory to implement if you need to have access to full scheduling properties in your firmware. If you need to run several tasks and your system is multitask and relies on, for instance, a preemptive scheduling based on a timer interrupt. And so you will have to implement these specific timers. And usually they have the same design. It's a counter value decremented at a given frequency, and you can change usually this frequency with some scaling register and so on. And again, you have access to existing implementation in QEMU. And furthermore, QEMU provides a rather simple API to manage time inside your simulation environment based on high precision timers that you have access in the host. So this is absolutely feasible. And it's no big deal that you have to do this kind of emulation in C code inside QEMU because the API is pretty simple to handle. And now that we have access ideally to a simulated environment inside QEMU, how can we try to find vulnerabilities thanks to our brand new simulator? And usually we will try to give a chance to some state-of-the-art fuzzer, like a coverage-guided fuzzer we can find publicly, like AFL, Anfuzz, or Syscaller, things like that. Even if they have been designed in the first place for user-learned applications, you will see that there are existing adaptations of this fuzzer for full system fuzzing. We have notorious examples such as Triforce AFL, Power AFL, or Gustav. So clearly, QEMU is a good landing pad for trying to fuzz full system with existing fuzzing engines. And so the basic strategy towards fuzzing would be try to simulate the board first and try to identify a location inside your firmware where the fuzzing will be interesting to begin. And to do that, you can take benefit of the dynamic debug environment provided by QEMU. It can be absolutely decorrelated from the device implementation inside QEMU, and you can guide the firmware to do some specific things using Python script connected to the GDB stub of the QEMU. So that's really easy to work like that. Even more, as you have access to the snapshot API of QEMU, you will be able to restore a full system image, memory and device memory too, to be absolutely deterministic for any test case that you want to try. So in the particular case that you're still missing the implementation of some specific devices, let's take, for example, the USB controller and some USB device in my CPIOM. I don't want it to be responsible for the implementation of such device. It was used once, and so it will take me a lot of time to implement that. But what is easy to do is actually try to bypass in the firmware the way the driver are trying to interact with the device. And so we can easily spot return zero function or things like that, that can be used to fix some function pointer tables to prevent the real driver initialization. And you can do that in a couple of lines in Python, trying to interact with the GDB server of QEMU. In this example, I can easily put a breakpoint at some specific location in your firmware when the USB is initialized and force a given value which was expected to be given by a USB device actually. And once I'm done with that and the firmware is able to go further in its execution, I can leave the GDB server and let the remaining part of my simulator continue. So we can benefit from both worlds. Now, if we have a look at how we actually do coverage guiding with QEMU, if you know how AFL works, usually you have to rebuild your target. When you want to fuzz something, you AFL need to inject inside the target some small shim to tell him what has been executed and to actually update its coverage trace bitmap. And if you have access to a binary firmware, you won't be able to inject this kind of AFL shim. And actually, QEMU can be helpful to that thanks to its TCG engine. And we will see that the way QEMU is able to translate instruction dynamically, you can take the opportunity to inject some tracing code to update, for instance, the AFL coverage bitmap. And so I will explain a little bit how the TCG work and what it is actually. The QEMU TCG stands for Tiny Code Generator. This is actually the JIT compiler of QEMU, which is responsible for translating, for instance, PowerPC of your simulated environment into an intermediate representation language specific to QEMU, which is then translated to your host instruction set architecture, usually an x86 or ARM machine if you're working on ARM. And so any guest basic block instruction and be translated in what they call translation blocks. And how these things happen, you have a main execution thread for your virtual CPU. And as long as QEMU does not need to handle some exceptional interrupts, it will try to find the next basic block to execute, the next translated block. And if there is no already translated block, actually will try to generate the intermediate representation and then translate this intermediate representation inside toward the host architecture. And this actually looks like that. If we have a couple of PowerPC, simple arithmetic, load and store instructions, they get translated into some simple TCG RR mnemonics, and then they get translated to the relating x86 architecture instructions. What we can see is that some of these instructions, for instance, from the Power PC, are not easily translated into native x86 architecture. And usually this is related to system level instruction. For instance, this move to MSR can't be translated to something equivalent in the x86 world. And to do that, QEMU relies on what they call helpers, and helpers are actually simple C code functions developed inside QEMU, which are responsible for emulating the behavior of the original instruction. And what the TCG does is that it injects a native call to the function that you implemented inside QEMU. And so in the end, you will be executing x86 code, but you implemented the behavior in C. This can be seen as a kind of para-virtualization of something like that. And for sure, we have seen that people, for instance, from the AFL++ project, and namely Andrea Ferraldi, took the opportunity to use that kind of TCG helper to implement the code coverage inside QEMU to report it back to. And in this example, we see that anytime QEMU needs to generate a new basic block, the code will be responsible for generating a unique index and a call to a specific helper that will be responsible for the code coverage. And the mechanism looks pretty much the same that a standard helper. A call to a specific function, for in this case AFL maybe log, will be dynamically called with the related index, and you will be able to update the AFL bitmaps from the QEMU code actually, and so with no specific overhead, a little bit like what you would achieve by rebuilding your initial target with the AFL shim. And so we see that deep diving inside the TCG allows to do some very interesting tricks. And the other point is, beside coverage guided fuzzing, if we need to do some fine-grained memory filtering inside QEMU, what can we do? What can we do with QEMU? If we look at existing example, we know that AFL Unicorn has for the user long part something called word pages, and they're able to overload some basic memory operators like malloc or free, something like that. You also have an address sanitization implementation for QEMU done in AFL++. And so it appears that there are not that much things available for full system simulation. And for sure, we won't be wrapping any memory allocation primitive inside your target firmware. And is the right way to do that maybe to have a look at lower level and interacting with our hardware page mapping or things like that. And if we look at the state of the art, Brandon Falk did some amazing things with fuzzing, and he developed a vectorized emulation MMU, which has a byte granularity and is able to detect an initialized memory access and things like that. So we really think that this is an interesting approach, and are we able to do such kind of thing using QEMU, and easily actually. And so what we need is that we want to monitor any guest kernel memory accesses, whatever the architecture or the execution mode. It might be an application, or it might be the kernel itself, or another specific mode, with the finest granularity possible, namely a byte access should be detected. And if we do that, we might need to define what's a legitimate access first. I mean, we need to define an exclusion zone of legitimate memory areas that you are able to access from illegitimate one. And for sure, we can have a look at TCG helper, and especially the way QEMU handle memory access and every memory operations that happen in the guest. How QEMU manage to write something somewhere when it is emulating the software. And if we look at a store word instruction, for instance, for the PowerPC, it will be translated to its intermediate representation and then to its final TCG backend operation, TCG out QEMU, which will be translated to a native x86 in our example instruction, doing the real access to your host RAM. And so QEMU define some kinds of virtual translation leukocyte buffer for its virtual CPUs, which are responsible for giving translation cache from the guest physical address to the host physical address. And ideally, this code looking for the TLB and getting access to previously translated addresses is absolutely in line with the memory access, the final memory access. And so they define two ways to access the memory. One is called the fast pass, which is what I explained. If you already have access to a translated address, you will end doing the memory access directly. And if you don't have the translation already done, you will simulate what's happening in the real hardware. You will call the MMU, and in this case, you will call the QEMU software MMU implementation to parse the page tables configured by your guest kernel and fill the virtual TLB inside QEMU. Fortunately for us, there are a lot of example MMU implemented, software MMU implemented for the PowerPC and for the architecture too. And so if we look again, the TCG out QEMU instruction will try to load the TLB entry. And if it happens to find this cache and this final target address, you will have the direct access to this memory location in x86 assembly code with no overhead actually. And if it does, it will go through the slow pass if it doesn't. So what has been done in our Gustav tool and how we can get inspired by this memory filtering mechanism, by this memory operation mechanism inside QEMU to do some memory filtering. And we can mimic the implementation with specific calls to filtering helpers. And in every low-level QEMU memory primitives, we will implement a call to our filtering mechanism. And this way, we will be able to detect and actually classify any memory access that happened inside the guest. And to do that with no overhead, as we were targeting a 32-bit system, we observed that we can define a kind of filtering memory bitmap, which is occupying 500 megabytes of memory with 1 byte on a 1 bit representation, which means that we can, with 500 megabytes, represent the 4 gigabytes full 32 bits address space on such systems. And so we can have access in a constant time to any byte which is accessed by QEMU actually. We implemented a kind of learning phase to be able to let the system run and trigger some memory access that we classify as legitimate, but you can also fix this memory filtering bitmap statically on your own, based maybe on some ELF information from your kernel or things like that, whatever you want. And anytime there is an illegitimate access to the memory location, we can trigger a guest panic state inside QEMU to help the further classify the test case as a crash one. And so it really looks like the standard QEMU fast pass implementation, and with an additional call to a specific memory helper, which is only looking in a red zone area. And whenever we detect such illegitimate access, we can change the running state of the guest. Two more useful features that you can have in QEMU, especially when speed matters and you want to implement some static and a very specific behavior inside your board implementation. Nothing that you want to do apart the simulation with a GDB server, for instance. Namely, if you want to inject inside the guest memory the test case provided by AFL, you can easily have access to the read-write API from QEMU to control the guest memory. You can even define internally inside the QEMU breakpoints, and without the need to start a GDB server. And this is really interesting. Actually, how software and hardware breakpoint are managed inside QEMU, usually they generate exception. But if QEMU detects that the breakpoint is not related to something happening legitimately inside the guest and has been added externally, for instance, using a GDB server, it won't be injecting the related exception inside the guest. And what it will do is that it will kind of notify a debug request inside the main loop, the main event loop of QEMU. And this gives you the opportunity to detect that such a running state, and especially a run state for the debug purpose, is being raised. And what you can do in QEMU is that you can not only easily add breakpoints internally, but you can also define your own VM change state handler and be aware of any state transition inside your virtual machine, whether it's related to debugging or restoring a snapshot or shutting down the system or things like that. And you can see that in this code, you even have access to the special guest panicking triggered when you try to access an illegitimate memory area. And so as a conclusion, I would say that QEMU is definitely worth it. It's a relatively big cost entry, but you have access to an open source software. You can look at the code. You have a huge community, a lot of mailing lists. Maintainers are clever people and open to discussions. And now you also have these little blogs with some hints for security researcher. So don't hesitate to hit our resources at AIRBUS Tech Lab, and I thank you in advance for your attention if you have questions.
Thank you, Stephane. We have one question. I'll read it out for you. But friends, if you have any more questions, please send them across via the Zoom chat. The question is from Ashmita. What challenges you think from bare metal perspective? According to you, what should be preferable approach when dealing with black box bare metal raw binary? Should we dig into QEMU or Unicorn that's on top of QEMU from the CPU emulation?
That's an interesting question. And as I said, it depends on your approach. If you know that your bare metal binary is doing some complex stuff regarding a complex Wi-Fi stack or something like that, maybe you can do a little bit of reverse engineering, extract this component, and give a chance to Unicorn and AFL Unicorn to especially fuzz this specific function. But it's providing the fact that you are able to extract and reverse engineer your firmware and so on. But I would say that having the ability to fuzz or to assess the security of a full system, as I said, enables more complex scenarios. And it actually depends. If the hardware is too complex, like we can see in modern SOC, maybe you will struggle at implementing the device simulation. For instance, it's really complex to simulate a GPU, for instance. But maybe you can bypass some specific devices, try to implement some really important devices too, namely the timers, the intercontrollers, to give a chance to the firmware to reach an interesting point and start fuzzing from there. And if you're able to fuzz the system as a whole, you will be able to fuzz not only specific function inside the kernels, but also simple application that you will struggle to run outside the firmware in AFL Unicorn, maybe if it depends on 1,000 of open file descriptors or specific sockets or whatever interface you might have with your specific kernel. So it depends, I would say. It depends.
Thank you, Stephane. Any other questions from the audience? Okay, Stephane, I don't see any more questions coming in. But friends, this webinar is recorded and it will be uploaded on our YouTube channel for future views. Most of the links, the tools that Stephane mentioned are there in the webinar presentation as well. So you all can refer to that later on. So thank you so much, Stephane. We really appreciate you joining us and sharing with us your learnings today. Thank you.
Thank you for the invitation and see you.
See you, everybody. If you all like today's webinar, please send us the feedback. Please also send a shout out to Stephane for sharing his knowledge with all of us on social media. And see you next week for another webinar from hardware.io. Thank you, everybody. Bye.